Hello. Today I would like to discuss uh, two topics. One is Hamiltonian principle, and another one is Lagrangian equation from the Hamiltonian principle. So let us start with the Hamiltonian principle. The Hamiltonian principle states that for conservative system for holonomic, its motion from time t1 to time t2 is in the form of a linear integral. So the principle states that states that for a conservative system, for holonomic, its motion from time t1 to time t2 is in the form of line integral. So I'm going to define that one as equal to integral t1 to t2 L dt. Okay. So this is equation number 1. Here L is L equal to t minus v. Has stationary value or I would like to give this one the extreme value for the correct path motion. Correct path of the motion. The quantity S is known as Hamiltonian principle function. The principle may be expressed as like this: delta t1 to t2 L dt equal to 0. This is equation number 2, where this symbol delta is the variational symbol. Okay. Now we are going to derive the Lagrangian equation from the Hamiltonian principle. So this is Hamiltonian principle. Now I would like to uh, derive this Lagrangian equation from this Hamiltonian principle. Okay. The Lagrangian L is a function of generalized coordinates and generalized velocities and time. Lagrangian L is a function of generalized coordinates, generalized velocities, and time, right? So here I'm going to expand this equation like this. L means Lagrangian, Q1, Q2, and so on, Qk, and so on, Qn. Sorry, here we need to write N. Q1 dot, Q2 dot, and so on, Qk dot, and so on, Qn dot, comma T. If the Lagrangian does not depend on the time explicitly, then this Lagrangian may written as a different form. So here note one important note here, that is, if the Lagrangian does not depend on time t explicitly, then the variation can be written as like this. Variation symbol delta L summation k equal to 1 to n dou L divided by dou Qk the partial derivative of dou Qk plus summation k equal to 1 to n partial derivative of L divided by partial derivative of velocities, partial derivative of variation delta z. Now our aim is to derive the Lagrangian equation from this Hamiltonian principle, right? So integrating both sides from time t1 to t2, that means integrating both sides of this equation from time t1 to t2. So that means the t equal to t1 to t equal to t2. Integral t1 to t2 delta L dt equal to integral t1 to t2 summation k equal to 1 to n dou L divided by dou qk into dou q dt plus integral t1 to t2 summation k equal to 1 to n partial derivative of L divided by partial derivative of velocities. Q dot means velocity, right? That's it. Now we know the Hamiltonian principle. Delta integral t1 to t2, right? L dt equal to 0. Okay. So therefore write down this equation t1 to t2 summation k equal to 1 to n partial derivative of L divided by partial derivative of q k partial derivative of qk into dt plus integral t1 to t2 summation k equal to 1 to n partial derivative of L divided by partial derivative of velocities dou qk into dt equal to 0. Okay, so I'm using this here the Hamiltonian principle. Here I'm going to give the equation numbers. The equation number 2. And one more parameter I'm going to write here, the where this velocities partial derivative of q dot k equal to d by dt of delta qk, right? So in equation 3, if you look the second term on the left hand side, so we're going to get this one. Okay, carefully if you look at here the integral t1 to t2, this equation, the second term, okay, summation k partial derivative of L divided by partial derivative of velocities qk dot dt. This one is expand this one, integral uv, okay, dt summation will get this equation u, this is dv, right? Okay, integration differentiation cancel, then we'll get the value. Okay, this one, right? Partial derivative of dk partial derivative of qk t2 to t1 minus integral summation k dy dt into partial derivative of L divided by partial derivative of velocities remaining this term. Okay, this one is delta q dot delta dt. This is equation number 4. The fourth equation we got, right? Now I'm going to draw this diagram here, the situation. Okay. This one is y-axis, this one is x-axis. So this is time t. This one is our position dots. Okay, q dot. Suppose qk at the time t1, the system is here. qk2 time, the system is here. These are the our two systems. So this is our situation. This is point A. This is point B. And this is point B. Okay, I'll just give me a minute. So just give me dot points, that's better. Okay, this is the positions. This one is at the time starting t1. This one is at a time t2 position. Here this straight line is there, right? This is the extreme path. This one. This is the extreme path. Extreme path. And this is our the varied path. This is our varied path. And at time t, position of the system is like this. This is t1 position. So this variation delta q. This is p dot. This is p. Okay. This is a position. This is b position. At the end point of the path, at the time t2 and t1, then the coordinate must have the definite values. These are the QKT1 and QKT2 respectively. That means delta QK of T1 equal to 0 and delta QK of T2 equal to 0, and hence so our term, this term is going to be 0. Okay, that means summation K partial derivative of L divided by velocities delta QK in between interval T1 to T2 equal to 0. Then equation number 4 becomes like this: integral T1 to T2 summation K partial derivative of L divided by partial derivative of velocities delta Q dot dt equal to minus integral T1 to T2 summation d by dt, the remaining term, that's it, nothing else. Partial derivative of L divided by partial derivative of Q dot delta QK into dt. Now we'd like to rearrange this equation. Dot is here, we're forgetting actually, right? Okay, now try to rearrange this equation, we'll get the Lagrange. So here I'm going to write this equation like this: T1 integral T1 to T2 summation K partial derivative of L divided by partial derivative of QK delta QK into dt minus integral T1 to T2 summation K d by dt. Just I'm rearranging the what we get the final equation, that's it. K into dt equal to 0. Okay, or else you just write down here that directly from the equation number 3. Equation 3 becomes like this directly, no need to write this step. So from this information I'm going to write this equation summation K integral T1 to T2, so minus common d by dt partial derivative of L divided by partial derivative of velocity minus here dou L is a dou Q into these two terms are there, right? Write down these two terms, QK dt equal to 0. Therefore this equation becomes like this: for Hamiltonian system, the generalized coordinates, delta qk's are the independent of each other. Therefore, the coefficient of delta qk must be vanished. So finally, we'll get this equation: d by dt into partial derivative of L divided by velocities minus dou L divided by dou Q K equal to 0. So this is our Lagrangian equation from Hamiltonian principle. Where the K is a 1, 2, 3 and so on. If you want K value 0, sorry, not 0, K will not start 0, K equal to 1, K equal to 1, 2, 3 and so on here. So this is called the Lagrangian equation of motion from the Hamiltonian principle.